Hello and welcome. You're listening to the University of Queensland's Astrophysics Group's podcast. Be sure to check back as often as you can for up-to-the-minute astronomical news and research happening both within the group here at UQ and abroad. For more information, visit our website at smp.uq.edu.au or send us an email to astrogroup@uq.edu.au. Today we have UQ's Dr. David Parkinson, who is undertaking the not-so-simple task of redefining our understanding of gravity. So let's see what he has to say.
Einstein's big idea was to link gravity with geometry. In the 17th century, Newton's law of gravity predicted the motion of planets round the sun, and also predicted the apples falling off trees or whatever. But it had no explanatory power. It didn't explain why that form of the force was required. But by Einstein's time, at the beginning of the 20th century, Newton's law was already failing. It was failing to predict the orbit of Mercury around the Sun, and so astronomers felt perhaps that there was some undiscovered planet, that there was something inside the orbit of Mercury, which they called Vulcan, which was disturbing its orbit and causing it to violate Newton's law, or apparently violate Newton's law. Einstein's theory of special relativity, which he formulated first, made a link between space and time. It said that they were in fact one thing, phenomenon of one thing, which he called space-time. And then his law of gravity, general relativity, all that stated was that space-time was warped by massive objects. So if you have particles moving through space freely, their world lines through space-time will become tilted towards massive objects, and they will move along these curved geodesics under the influence of gravity. So Einstein's theory had an explanatory power, and it also made some predictions. It predicted the motion of Mercury, and it made other predictions which were then backed up by experiment. And in this way, it was one of the most successful physical theories of the 20th century. But then in the sort of 1980s and 90s, there were problems, holes emerging. In particular, it couldn't explain the motions of stars around galaxies and the expansion history of the universe, the expansion of galaxies away from one another. And in order to prop up the theory, astronomers invoked the existence of dark fluids, things like dark matter and dark energy. But they basically found themselves back in the same situation as before. They had motions of particles which they couldn't explain, so they had these undiscovered things causing them to move differently. But could it be that once again our theory of gravity was at fault? So F of R gravity, the modified gravity theory, is like GR, but it has an extra term in it. It's geometry again. It's all geometry again. So the Einstein-Hilbert action is just the integral of the Ricci scalar. The Ricci scalar is a geometric concept introduced in general relativity, used in general relativity to make the equations work. In F of R gravity, all you do is you take the standard Einstein-Hilbert action and you add in an extra term, a free function of the Ricci scalar. Once you specify what F of R is, you vary the action with respect to the metric, you recover the equations, which will become modified for what you get in general relativity, and then you can work out the expansion history of the universe, the orbits of stars, etc. So the main thing, once again, you have a problem though, because you have to explain everything that's gone before. You have to explain all the orbits that we see in the solar system, all the solar system physics, as well as explaining things on cosmological scale. And because of general relativity, we know it works on solar system scales, so we have to introduce a scale. Some scale where we go from the theory, which is just the R term, the GR theory, to our expanded theory. And this scale will imprint itself on the structures of the universe. We'll get a expansion history that looks like the same kind of thing, but we'll get these structures evolving differently on different scales. And so this will leave an imprint, basically. And by examining the distribution of galaxies, clusters of galaxies, even larger things, size of the Great Wall or whatever, and looking for this imprint, we can try and determine what the best theory of gravity is for the universe.